Now we want to introduce and start talking about a little bit the idea of an average rate of change. It's an idea that's very important in calculus. In some sense, calculus just is the study of rates of change. So let's write that. So we want to study what the average rate of change is. And we're talking about functions, so let's look at the average rate of change of a function. And let's start with an example. Let's look at what average speed means. So this is something that we're kind of familiar with, okay? So we want to study average rate of change, and we're looking at speed. Remember, what is speed? Speed is the rate of change in location. So speed is just an example of a rate of change, and it's one that we're really familiar with. So let's just think of an example. So maybe there is a person, and they are starting at a certain place, and maybe they're running, or I don't know. So here's the starting location. Okay, so let's just call this location 0, and then they're going to walk or run, and they are going to finish later. Let's say that they go, what do you want to say? Let's say they go 100 feet. Okay. Alright. So let's make a graph of their location and time. So I'm going to graph distance from the start is what I mean by location. So I'm going to graph distance from the starting place with respect to okay, so let me explain even more what I'm saying here. I'm going to define a function f, which is a function of time. F is going to take time as an input, and when you put the time in, it's going to output the location of the man from the starting place at time t. Okay, so it is distance at time t. And there are lots of plausible answers for what the graph of f might look like. We just have to make one up. So what's going on here? Alright, so the x-axis here is time, and we said the y-axis was going to be distance. So anytime you have a function, the horizontal axis, the x-axis, is the input, and the y-axis is the output. So that's what's going on here. Okay, so we know that at time 0, the man is distance 0 from the starting place, right? Look, he's standing there at time 0. He hasn't gone anywhere. Okay, and we know that some time later he ends up over at the finish, which is 100 feet away from where he started. Maybe we should make a little notch here on the y-axis to indicate where he finally stops. Okay, so let's say that this is 100 feet. Okay. And this time, let's use the units of seconds, and on distance it looks like we're using the units of feet. Alright, so I'm just going to make up a curve. The curve could look kind of crazy, right? Maybe the man is nuts, and he runs forward for a while, and then he runs back again. And so if he does that, he's going to go away from the start, and then he's going to go back towards the start, right? And it's going to be curvy. And so the curve could be really complicated, but let's say that he is in a race, or he's sane, or he knows exactly what he's going to do. And he does something nice and simple. So he starts out at the origin, and he runs and runs, and here, okay, so this is the time at which he finishes. So this is the time at which he finishes. And just so we can work with concrete numbers, let's say that to go that 100 feet, what's a good number? 30 seconds? So it took him 30 seconds to go that 100 feet. Alright, so now the question that we want to ask ourselves is what was his average speed? Okay, so how could we do that? So it's just how far he went divided by how long it took. Okay, and there's no way to reason that out. That's just the definition of what average speed is. So average speed is equal to distance gone divided by time taken. Okay, alright. So first we're going to look at that in this particular situation here. So we know that he went 100 feet and that it took 30 seconds. So this man's average speed is 100 divided by 30. So we can knock that off, right? So it's 10 divided by 3. And notice that up here in the numerator the units are feet, and in the denominator the units are seconds. So the units for speed end up being feet per second, which makes sense, right? Because that's a unit for measuring speed. So his average speed is 10 divided by 3 feet per second. Alright, so what does that have to do with this picture? Because this picture is a graph of distance, and so distance is the output and time is the input. So what speed means graphically, so the average speed, what it means in terms of this picture, it's the slope of this line. Okay, so graphically, average speed is the slope of this line. And sometimes we call this the secant line. When we draw a line connecting 2 points, the technical term for that is the secant line connecting those 2 points. Alright, and so let's just say a little bit about why that's true. I can't just declare that it's true if it's not really true. So why should it be true that the average speed is the slope of this line? It's because slope is rise over run, right? So slope is rise over run. And so what is the rise? Well, the rise is how far he went, right? So the rise is 100, and the run is how far we go over, and so that's how long it took him, which is 30. Okay, so that's always going to be true. So it's always going to be true that if you want to find the average rate of change of a function between 2 points, it's just going to be the slope of the line connecting the 2 points. So let's try to express that. Okay, so here's the idea. Okay, so the average rate of change, just think of it as the speed if you want, of a function, any function whatsoever, so let's just call it f, and now f is just standing for any function, between x equals a and x equals b is, okay, so we said it was the slope of the line connecting the 2 points, and what is that? That's always just the rise over the run. Okay, so let's look at that in a more general situation here. So here's the curve given by f. Okay, and let me draw some axes. So this can be the x-axis, and here's the y-axis. Okay, so we want to know about the average rate of change between some x value a and some other x value b. So here is b. Okay, So how are we going to express the slope of the line connecting the two? Okay, so the average rate of change is the slope of this line. So to know the slope of that line, we need to know its rise and its run, right? So look at this. All right, so here is the run. So the run, and we might also call this the change in x. Okay, so this is how much x changes, this delta thing, maybe you've seen it in high school and other places. We write capital delta to stand for change. So the run, figuring out the slope of this line, is the distance between a and b. And so I'm going to write that as the symbol delta x. Alright, and we also need to know this, right? Because slope is rise over run. This is going to be the rise. And I'm going to call this change in y. Okay? Alright, so the slope of the green line has slope m. You can see that m is going to be equal to delta y over delta x. Okay, alright. So we're frequently going to be interested in actually figuring out what this is. Okay, so let's say that we know what the function f is. How do we figure out this thing, the average rate of change? So let's just figure out what change in y is in terms of f and what change in x is in terms of f. So let's do change in x first. It's a little easier. Okay, so here I've got this general picture, but in a particular problem I'm going to know what a is and I'm going to know what b is. So I want to be able to express change in x in terms of these two things that I know. And you can just see that this distance that is delta x, that's just going to be b minus a, right? Oh my gosh. The distance between a and b is just b minus a. These are just numbers, right? So if I had a line, and if this was the quantity 8 and this was the quantity 3 or something, then the distance between 8 and 3 is 8 minus 3 equals 5. So that's all I'm saying here. So delta x is b minus a, just like the distance between 3 and 8 is 8 minus 3 equals 5. Alright, and so how do we do a similar thing for the change in y? Alright, so you can look over here. So this is an interval on the x-axis, but the change in y is going to be an interval on the y-axis, right? So we can do the same trick if we know what these 2 points are. And okay, so this is a general situation. What is this? Well, it's this height, okay? It's the height that the function sends up a. And so just by definition, the height that the function sends a is f of a. Okay, and what is this height? This other height is how far the function sends up b. Okay, so the function sends b up here. So the y-coordinate of this point that I just highlighted here, the y-coordinate is f of b, just because that's what the graph of the function means. And so what that means is over here on the y-axis, the height is f of b, and that means this, the change in y is just f of b minus f of a. I know, like, the function f of b and f of a is kind of complicated, but this is just like the distance between 8 and 3 is 5. The distance between f of b and f of a is just the big one minus the small one. So it's f of b minus f of a. Alright? And so let's go back here and finish our statement. So the average rate of change of a function f of x between x equals a and x equals b, we're almost done. Okay, it is delta y over delta x, and we just said that that was equal to f of b minus f of a divided by b minus a. Okay, and so we're done. Okay, so we just defined what average rate of change means for a function. And later we can come back and do some other interesting things with it, but let's just stick with this for now. So that formula is what we just arrived at.